Hello everybody, my name is Niklaus Felderer. I would like to welcome you to this session on the topic Technologies for Hardware-in-the-Loop Simulation of Complex Power Converters. Now before we start, an important question is, what are the requirements for a successful hardware-in-the-loop test? And the answer to this question will also decide on how to approach the task of modeling complex power converters. Some of the main points here are the low input to output latency, so the simulator should respond in a fast way. It should also respond in an accurate way, so really according to the stimulus that's applied. And it should also provide enough flexibility to be able to emulate the power converter in different operating points, including fault conditions. There are different levels on which one can tackle these 3 points. On the model side, the most important one is the implementation of switching devices. Now, clearly, modeling a system with a linear transfer function will reduce computational effort and decrease the time for the Hill simulator to respond to an applied signal. However, the accuracy and flexibility is not enough for what is needed in a hardware-in-the-loop setup. One level below that, one could call the circuit level. One also includes the large signal behavior of the semiconductor devices. So that means the switch is really represented in an on and an off state. The most detailed level contains component level specific features such as, for example, Miller plateaus in MOSFETs or reverse recovery in diodes. And this level is not suitable for hardware-in-the-loop simulations as the required time constants are in the pico to nanosecond range. And also closed-loop control testing is not mainly focusing on these component level features. Working on a system or circuit level, what are the possible switch models that can be utilized? Now, here we only discuss a very small subset of all the possibilities, but a very simple and common approach is to use a dual value resistor model, where the switch is represented by a small resistance in on state and a very large resistance in the off state of the switch. And the drawback of this is that it requires a snubber circuit. That means we need the series connection of a resistor and a capacitor in order to be able to implement this model in a simulation software. And this virtual snubber circuit really does not reflect any physical behavior of the switch. Now there's another approach, which is the Pejovic model, where the switch is replaced by an inductor in the on state and a capacitor in the off state of the switch. Here, no dynamic snubber is needed, but still a virtual resistor R has to be properly chosen, which is also depending on the step size that's later used on the real-time simulation platform. Now, the Pejovic model is a very nice approach for the modeling of, for example, diodes, but both the dual value resistor model and the Pejovic model suffer from an artificial transient behavior around the switching instant. And this can be seen here in this boost converter example, where at the switching instance, there is a certain transient that is not really given by any physical behavior of the switch, but that is just occurring because of this virtual snubber circuit that's needed. Now, because of this artificial transient, we also need a fairly small step size in simulation. Now, the third possibility is to use an ideal switch approach, where the mathematical description, or more specifically in this case the state space description, is dependent on the active switching combinations. So here we have the example of a buck converter, where we have two switches and there are two states of the switches shown. Once a diode is conducting with a blocking switch, and once with a conducting switch and a blocking diode. And each of them will have a different state space description. Now, in an ideal switch model, the off state of the switch is not represented by a very large resistance, but actually by an ideal open circuit with an infinitely large resistance. This means the switching transient is reduced from what we here see on the left, this real transient, to a transient that's basically only occurring at one discrete point in time. This model is very much suitable for hill simulations because it does not show any of the artificial ringing around the switching transient, and therefore the step size can be larger compared to the other methods. However, one drawback is that the number of state space matrices grows with 2 to the power of n, where n is the number of switching devices. So especially when we have topologies and circuits with many switching devices, this complexity can become a problem. So how can the ideal switch model now be utilized to simulate complex power converters, and what does complex, the word complex, actually mean in this case? Now there are different complexity factors. For example, how many switches are there in a topology? The more switches, the more complex a certain circuit operation can become. Also, how often do they switch? Real-time simulations need to employ a fixed time step. So how does this fixed time step or the step size relate to the switching frequency that's applied? And also, how do they switch? That means, is it a forced or a natural commutation of current? In that sense, if we look at the two topologies given here on the bottom, then we have this 5-level inverter, which in the end has kind of a similar degree of complexity as this dual active bridge, because the dual active bridge has a current that commutates on the base or the time base of the switching frequency, and this makes it much more complex topology to model than if we look at, let's say, a simple inverter operation, even if this is an inverter with, let's say, 5 levels in this case. Now, the first problem of the number of switching devices can be overcome by so-called hybrid modules instead of a fully switched converter model. And this can be seen here on the left, where we have series connected full bridges. So here we have basically 8 switching devices, and we reduce that to just a pair of 2 diodes, which distinguish basically the current or the direction of current flow at the phase output terminals, and the rest is implemented with controlled current and voltage sources. And what this means is that instead of actively trigger a swap or recalculation of state space matrices, these switching signals, they now become an input to the state space description. Now please note at this point that the model dynamics of the switched model and the hybrid model, if used in an offline simulation with a variable time step solver, is exactly the same. So they're absolutely equivalent. There is no difference basically between the two. But what is nice is that we can reduce the number of switching combinations or the number of switches that are needed to model these series connected full bridges from 8 to 2. Now the second problem when we look at the fixed time step execution of a model in a real-time simulation platform can be overcome by time averaging the switching signals over one simulation step. This can be seen in the case of a buck converter simulation given here on the bottom. And instead of taking the actual value of the switching signal at a simulation step, one can use time average switching signals S bar to accurately represent how long a switch has been in on and off state during a simulation step. This can be seen in interval T3 to T4, where the time average value at T4, marked in red here, accurately represents the on time of the switching signal in this period. So a hybrid model with a time average switching signals performs better than its purely switched counterpart if we run this model on a real-time simulation platform with a fixed time step. The last problem that I mentioned initially of the natural commutation of current can be seen in the plot in the middle. Here the diode turns off in the interval of T7 to T8, but one can neither guarantee that the simulation step coincides with a turn-off transition, nor actually calculate the time of the switching instant without knowing the external circuitry. This becomes especially a problem in DC-DC converter topologies, where the current commutates on a time base given by the switching frequency and not, for example, a slower mains frequency. So here we can see in the interval T7 to T8 that we actually miss the exact turn-off instant of the diode. So to tackle this third problem, one really has to include the inductive circuitry that's connected to the switching network to calculate the exact zero crossing of the diode current. In case of a dual active bridge, the hybrid module of the two full bridges is extended to also include the inductor, or actually the calculation of the inductor current. This model has as inputs the time average switching signals and the DC side voltages, and as output the AC current through the inductor. Let's now make a specific example where we assume that the current through the inductor IL is positive and the secondary side of the dual active bridge is not modulated, for example, representing a fault scenario. In this case, assuming a winding ratio of 1 of the transformer, one can calculate the voltage applied over the inductor, which is negative in this case. If the inductor current is positive and the applied voltage is negative, this means that the inductor current is passing through zero at some point. And the problem here is that the applied voltage will change as soon as the current crosses the zero line. That means that the estimated simulation result of IL at the simulation step k+1 is not valid anymore. So this means the current is recalculated by taking into account how long the individual voltages have been applied to the inductor during one simulation step. So basically this means, given here in the graphics, we need to see what changes, or how does the applied voltage over the inductor change in the phase TR, and how does this result need to be adapted according to this applied voltage. This can be seen here. So now when we assume that the inductor current is negative, then we also see that we have a different applied voltage to the inductor, and instead of having this old simulation result of IL of k+1, we need to recalculate this current. And this means, for example, that the slope of the current changes within that simulation step. Now this is just a very specific example, and there are many more events, possible events, occurring during this or during one simulation step, also in different topologies, of course, so that this method of extending the hybrid module to include a certain physical state, in this case it's the inductor current, this is called a substep event module, because it treats basically these events even within one simulation step. Okay, so now let's see how we can deploy this substep event module on a real-time simulation platform. And for this reason, I've prepared here a model in the simulation software Plex. And this consists of a controller and a plant model. The controller consists of a PWM generator, and we only generate PWM signals for the primary side, so 4 signals in total, all with 50% duty cycle, and 2 of them are phase shifted by 0.75, which is per unit. Then as a switching frequency, we have 100 kilohertz. And now let's look into the plant model. And this actually does not only consist of one model, but actually 3 models in total. So there are different configurations in this configurable subsystem. Once there is a switched configuration, which in an offline simulation and with a variable time step solver will be our reference solution. Then there is a hybrid module, and then there is the substep event module. And we're going to now compare basically all 3 models for this switching network, for this dual active bridge, and see how they actually perform. Okay, so let's now first generate or simulate the reference solution. And this means we're going to choose the switched configuration. for our dual active bridge. I'm going to simulation and then start, and then we can already observe the results of the offline simulation in our scope. So this is still just an offline simulation in the desktop simulation software, and as we're using a variable time step solver, this will be our reference solution. All right, now you can see our real-time setup in the lower right corner. There we have an RTBox CE, the small box on top of an RTBox 1, the bigger box, and the RTBox CE is going to be our controller, so generating the PWM signals, and the RTBox 1 is going to be the unit that simulates our plant model. And first we need to select our PWM capture unit. So this means we're going to use time average switching signals. I'm also going to select hybrid module for the dual active bridge configuration. And now we're going to deploy this configuration on the real-time unit, so the RTBox 1. I'm going to the coder options, and there are the two possible systems to deploy, which is the controller, and this is running at 10 microsecond step size, which corresponds to 1 over the switching frequency of 100 kilohertz. I'm selecting here the target device, which is our RTBox CE, so the top device, and by clicking the build button we can generate code and we can upload the code to the target. Once the target is programmed, you will see a blue LED lighting up, which is now the case, and this means now our control code is running and PWM signals are generated. We're doing the same for the plant model. Here I select the RTBox 1, which is the bottom unit, to be programmed, and again we click the build button and we're going to download the plant model to the RTBox 1. So with this programming we can then actually check what are our real-time simulation results for this hybrid module configuration. So the RTBox 1 is now running, and we can go to the external mode, connect with the real-time unit, and then stream the real-time simulation results into the same scope as we have saved our reference solution in. Okay, so now let's activate auto triggering. And you can already see from this zoomed out view into the scope that the real-time simulation result we get with the hybrid module is absolutely inaccurate. So you can see that the positive or negative half cycles are not properly calculated because we do miss this switching of the diodes, and therefore we cannot properly represent this circuit in this operating point. I save again a trace and call it the hybrid module simulation result. All right, so let's disconnect now from the external mode so that we can change our offline model again, or our simulation model, to the substep event configuration. I click again on the build button to load this new configuration onto the RTBox 1. You can see that the blue LED lights off, and then once it is programmed it will light on again. So now we can connect again to the external mode, and now when we zoom in we can see that we already have both half cycles properly represented, and by adjusting the trigger level and the trigger delay we can get a very nice overlay of the real-time simulation results with the reference solution. So when we save a trace, we have now a static or a snapshot of our simulation result, and you can see that the substep event model perfectly coincides or overlays with the reference solution from our variable step offline simulation. So let's label this as substep event configuration. And to make the comparison even a bit more clear, I select the display of the real-time simulation result as impulse. And by doing this, you can see that we really exactly hit the calculated values of our offline simulation with this sub-step event model. We can also change the colors quickly so that we have a better comparison between the different simulation results. So in green, you have the reference solution. Then we have in red the sub-step event module. And then we have in blue our hybrid module result, which obviously is incorrect. All right, so there you have it. I hope you found this presentation useful. First, I gave you a quick overview on the different modeling approaches for switching devices and switching networks. Then we discussed a few options on tackling these different modeling approaches for the switching devices on real-time simulation platforms. And then we also discussed a very practical example of the dual active bridge and the implementation on a real-time simulation platform. Thank you very much for listening and have a good day.